Alright, so my name is Bree Abbott, and I am in Bio 201, and I am doing the crossed extensor reflex for my modeling project. So we'll start with the easy version before we go into the deep anatomy of it. So Bob is walking along, and a rogue Lego comes out of nowhere, and Bob, unfortunately, steps on that Lego. Bob, however, doesn't feel the pain right away. What happens is his right leg begins to flex, so it starts to move up. That way he's not stepping on the Lego anymore. And his other leg, the opposite leg, is extending. Therefore, Bob, he doesn't fall over and he stays more balanced. It's not until after all of this has occurred that Bob feels the pain. Ouch. So, let's see what really happened to Bob. So, as Bob was walking along, he stepped on the Lego. And the leg with which he stepped on the Lego is called the ipsilateral leg, while the other leg is called the contralateral leg in the reflex. These names are given because the leg that Bob did not step on the Lego with still reacts to the stimulus because it's extending, while the ipsilateral leg flexes in order to turn off the stimulus, or the Lego that is causing him, pain that he stepped on. So, flexor muscles in the leg, flexor muscles are used in regards to the leg being flexed, or the ipsilateral leg. These muscles are what receive the message from the motor neuron, and therefore the leg becomes flexed. So it raises up. That way he can step off the Lego. And the extensor muscles do the exact opposite. These muscles are present in the other leg that's extending in order for Bob to maintain his balance. Without these muscles, Bob would indefinitely fall over and many other reflexes would occur. But we're not going to get into that right now because luckily Bob's muscles seem to be in working order because Bob did in fact not fall down. He just felt some pain. So now knowing that Bob does not fall over, let's get into the technicalities of crossed extensor reflex. So this reflex cannot occur with just one type of neuron. Many things are going on, and many things have to happen before the pain is actually felt, and all the pain receptors in the brain are activated. Because sensory and motor neurons are excitatory and two synapses occur, this is called a polysynaptic reaction. Impulses do not just come out of nowhere. On the neuron, impulses are created within the axon. When the Lego is stepped on, pseudopolar somatic sensory neurons are the first to be activated, and they send messages to both the brain and the muscle. These activate interneurons, which are here, which then move to the motor neurons. That way they can force the leg to extend or extend or flex. So these, the interneuron is sending waves down here, which is causing this muscle to flex this leg and this one to extend. The motor neurons are acting upon the leg because they pass through the ventral root, allowing the impulses to be shot to the muscle. Pain receptors in the brain are shooting out messages through the spinal cord, and the dorsal root ganglia acts as the link between the CNS and the spinal cord. This all seems like it takes a really long time, but this happens in a matter of milliseconds. So due to reverberation, or the continued impulses after the initial stimulus, positive feedback is able to occur. The original stimuli is increased, and the pain does not just stop immediately. Pain receptors do not send any signal to the brain until all other reactions have occurred and the flexion has already been done. By that, I mean that after the Lego was stepped on, sensory neurons, which are excited, shoot messages to the brain, and from the brain and the spinal cord, messages are shot, and motor neurons are brought to the muscles, therefore extending and flexing the leg. So Bob isn't going to feel the pain until this muscle flexes and this muscle extends. Bob should really watch where he's going next time because rogue Legos can appear out of anywhere at any time. Yeah.